Good. So in the previous lecture, we introduced what are called Lipschitz continuous functions, but Lipschitz continuity in one variable. Okay. So today's class we will see how the Picard iterations will converge. Okay. So this is known as the Picard's theorem. Okay. So consider the problem, the initial value problem. That is x prime t equals to f of t x. So either you can write x prime or y prime. So I'm taking x here as a function, which is a solution, unlike the previous chapter. Okay. So this is x at t naught equals to x. Okay. So where t naught x naught belongs to R. So you have this is the point and this is the point t naught. Okay. So what the Picard's theorem says is for given a point t naught x naught, okay, in R2 and let omega be a rectangle, or you can take a domain. So since they are the same, whether I take a rectangle or domain, I'll take a rectangle around this point. Okay, so basically we are looking at, so this is a rectangle around this point. So if f is Lipschitz in R, okay, Lipschitz in R, then the initial value problem has solution in an interval around t naught. So that means that you have a small interval around this point, so that this initial value problem has a solution. That means that you have something like this. Okay, so this is the curve which is passing through this and satisfying the differential equation. Okay, so this is and moreover the solution is unique. Is unique. Unique means that if you find two different solutions, you cannot find two different solutions. If y1 and y2 are the solutions of this initial value problem, then y1 is identical equals to y2. Okay, solution is unique means there is only one solution. So let us first look at some examples to see how this, what are the type of problems that we are looking at. Okay. So for example, let me start with y prime equals to say y square plus t square, y at 0 equals to 0. Okay. So this is, you see that in this case f ty equals to t square plus y square, and t naught is 0 and x naught is 0. And you know that this function t square plus y square, so if I take a rectangle R, which is the set of points ty with -1 less than or equals to t less than or equals to 1, and similarly minus 1 less than or equals to y less than or equals to. So this is going to be, okay, Lipschitz. F is Lipschitz on R. So the reason is that look at dou f by dou y, which is just simply 2y. Okay, so this is less than or equals to 2. Therefore, okay, so therefore f is ellipsis function on R. Therefore, such a problem will have unique solution. So this problem has unique solution. Okay. So the problem solution can be anything. We don't know. It has a solution, and the solution is unique. Let us look at another problem. Say y prime equals to sine y. Y at 0 is 0. Again, in this case, f ty, which is equals to sine y. Okay. So this has now, this is now Lipschitz everywhere. Okay. So this is Lipschitz in any domain around 0. In the whole of R also, the whole of R2. In any domain around 0, 0. Can be in the whole of R, because the derivative of this is cos phi, which is less than or equals to, always absolute value is less than or equals to 1. Right? Therefore, by the theorem, you have there exists a solution and it is unique. But you see from this equation, you see that y identically equals to 0 is a solution. Okay, y identically equals to 0 is a solution. And the equation has a unique solution. Therefore, y equals to 0 is the only solution for this equation. See, that is the only solution. That's what the power of this theorem is. So it says that there is a solution, and from the simple observation, we see, yes. Yes.
Similarly, in the previous case, also like in the previous example.
Your voice is breaking. Once again. Once again.
So we
No.
are
I'm not able to hear. The voice is breaking. Can you write in the chat box what your question is? Or can you try to speak again?
which we have is
No, I'm not able to hear. There is a big breaks in your voice. Yeah. There are big breaks in your voice. So can you write on the chat box what your question is?
Yes,
At least something you write, make out from there. Meanwhile, if anyone else has questions, you can ask me.
सर
Yes.
सर जैसे इसमें y इक्वल टू मतलब 0 सॉल्यूशन हुआ, तो सर इससे पहले वाले एग्जांपल में भी वही होगा ना, क्योंकि उसमें भी यूनिक सॉल्यूशन था.
Y equals to 0 is why it is a solution in the previous example. Y prime is 0, but so y prime equals to t square plus y square, right?
Yes.
Okay, so this kind of equations, which are nonlinear terms that you have here, even using this theorem, we can get some information about the solutions of this. Okay, and you can see the yeah, yes.
So, but the manual process, this y dash equals to sine y equals to by 0 equals to 0, has solution does not exist.
Solution does not exist.
Yes, sir. If we do manually.
What is the meaning of doing manually? I am saying can't you substitute y equals to 0 in the equation?
या सब्स्टिट्यूट करने के बाद मतलब कि केस ऐसा बन रहा है जो अनडिफाइंड केस बन रहा है.
कैसे? y prime equals to 0. If y is 0, y prime is 0. Sin 0 is also 0, and y at 0 is also 0, right? So 0 is a solution for this equation for this initial value problem, right? What is undefined here?
No sir, मतलब वो सेपरेशन मेथड से हम सॉल्व करते हैं, वो सॉल्यूशन फाइंड करते हैं, देन पुट द y
why every equation needs to have a solution by separation of variables method? Is there any reason for that?
No sir, but हम यहाँ लगा सकते हैं ना, इसलिए.
क्यों? It may not exist. The solution is 0, so there is no other solution. So separation of variables may not be possible in this case, right? That's why you are not getting any other solution.
Yes, now wait.
So separation of variables, see, any method that you study or you see, you have to see the limitations of that method, right? So the limitations are there for separation of variables. So you should be able to integrate that function in the neighborhood of that 0. So that may not be possible, right?
Yes, but this is not possible there.
If it is not possible to integrate, that means the method fails there. So that is it's not the correct method to use to solve the problem.
Yes.
Okay, so on the other hand, the Picard's theorem tells us that y equals to 0 is the only solution for this equation. Okay, so after these two examples, let me also give one more example. Say y prime equals to y square power 3 by 2, okay, or y power 2 by 3. Okay, and y at 0 is 0. So you can try to solve this. Can you try to solve this problem by using separation of variables, as somebody pointed out? So this is going to be dy by y power 2 by 3 equals to dt. So this implies, so this is y power minus 2 by 3 plus 1 on minus 2 by 3 equals to t plus c. Okay, so this is 3 minus 2, 1 by 3. So this is 3, and this becomes y power 1 by 3. Y at 0 is 0, implies c is 0. So c becomes 0. Therefore, y power 1 by 3 equals to t by 3. So therefore, y equals to t by 3. Is that fine? Or t cube,
yes,
t cube by 9. Okay, now I also know how to solve by separation of variables.
T cube by 27.
T cube by 9. Okay, good. Now you see that there is a solution y equals to t cube by 9 here, and also y also 0 is a solution. Y is identical equals to 0 is a solution. Right?
Sir, it should be t cube by 27.
T cube by
27.
Sorry. 3 cubes are 27. Yeah. Right. So also y equals to 0 is a solution. So this problem has now two solutions, at least. See that there are at least two solutions. So, and on the other hand, you see that y power 2 by 3, okay, is not a ellipsis function. This is not a ellipsis function. This is not a ellipsis function. Why is that? Y power 2 by 3 is not ellipsis around 0. Why is that? Suppose yes, by contradiction, there exists one L such that f of y minus f of 0 is going to be less than or equals to L into mod y. Right? So what is this? This is y power 2 by 3 upon mod y. Everywhere it is a mod is less than or equals to L. Now you take the limit y goes to 0. You get a contradiction. So when you take the limit y goes to 0, the right hand side is okay. LHS goes to infinity, but right hand side is remains L only. So this is not possible. So this is a contradiction. That is why this is this function is not an ellipsis function around 0. So that's what we are seeing here, that if it is a function which is not an ellipsis function, then there is a possibility of getting two solutions. Not only this, in this case, there are infinitely many solutions. Okay, so why is that? Look at the graph of t cube by 27. So this is t cube by 27, which looks like this, right? So the same graph, you can just translate it by a constant. So call this as a constant, any constant, say alpha, and then take it to be 0 here. Okay, so you will write y alpha t, which is equals to t minus alpha power by 27 for t greater than alpha and 0 for t less than or equals to. You can see that this is a differentiable function, satisfies this equation. And this happens for every alpha which is a positive real number. So that shows that there is not only infinitely many solutions, there are uncountably many solutions. Okay, so the solutions forms a continuum of there is a continuum of solutions. So basically, the continuum of solutions means for every real number there is a solution. Okay. So this is our aim. Our aim is to show either the problem has a unique solution. So this theorem is known as Kussner's theorem.
Sorry, sir, can you repeat?
I'm writing here. So what he says is that either you have a problem with a unique solution, or if the problem has two solutions, then there is a continuum of solutions. Okay. So we'll prove this a little later. We'll show that if there are two solutions, then there are infinitely many solutions. So there is nothing in between. There's nothing in between means that it cannot have just two solutions in initial value problem like this. Okay, so let's go back to our Picard's theorem. So this is what the Picard's theorem says. So let us try to give a proof of this. So I said previously, what is an equivalent integral equation? So what is an equivalent integral equation? So to get x prime equals to f t x, x at t naught is to x naught. Okay, so you can also write equivalently the x at t is x naught plus t naught to t f of s xs into x.
Sir,
Ah,
sir,
yeah.
can you please repeat the part why 2 by 3 is not Lipschitz function?
I gave a proof, no? I thought I gave a proof, no? Suppose if
Yes,
it
sir.
is Lipschitz. Suppose if it is Lipschitz, okay, by contradiction. If it is Lipschitz means that there exists a constant L, so that this is true. fy minus f0 is less than or equals to L into mod y. This is the Lipschitz condition. And then divide this relation by y. Okay, so divide by y. Then you get this relation y power 2 by 3 upon y is less than or equals to L. Once if we have this, we are saying that such a relation is not true in a neighborhood of 0. So take limit y goes to 0. So if you take y goes to 0, the left hand side goes to infinity. But whereas the right hand side is still L. So that is a contradiction. That's why this relation doesn't hold. This relation doesn't hold in the neighborhood of 0. Okay, so this 1 and 2 are equivalent, right? So 1 if and only if 2. So the proof I already said, if you have 1, just integrate to get 2. If you have 2, just differentiate this 2 to get 1. That's all, just by fundamental theorem. And let us also to show the existence of, so our aim is to show that there is a small interval around this T0 where the 2 holds, where there is a function x, so that 2 holds for that function. Okay, so let us assume that take a rectangle, okay, so which is, let R be a rectangle which contains the point t, x, where mod t minus t0 is less than or equals to a, and mod x minus x0 is less than or equals to b. Take a rectangle like this. Okay, take a rectangle like this. And since we are assuming that f is a continuous function, and if so moreover Lipschitz continuous function, there will be a constant m, which is the maximum of over R of this mod f dx. Okay, so this f is going to be bounded in the bounded rectangle, and let me call that as m, the bound on f. Also, let me define h is the minimum of a and b by cm. Okay, a is this, b is this, and m is this. Let us take h to be the minimum of this thing. So what we trying to show is we claim that there exists one x satisfying 2 okay in the interval t0 minus h to t0 plus h. So this is the small interval where around this point t0, where we can find the function x satisfying the 2. So that is our aim. So let us look at 2. How do we show this existence of x? So we'll show the existence of x as limit of is xn's, xn plus 1 or x k plus 1, let me write as k plus 1 t is equals to x0 plus t0 to t f of t xkt is xks. So dummy variable. Yeah. So define like this for k equals to 0, 1, x. So then these xk's are continuous functions. Okay, that's not difficult to show. And moreover, the xkt, right? So if I look at xkt, is well defined. Well defined in the sense that they're all functions. That is not difficult to see that this is actually, or if you put x0 in the side, what you get x1, which is now, since f is a continuous function, so the integral of continuous function is continuous, therefore x1 is continuous. So if you put x1 back in this, then x2 is also becomes a continuous, because composition of continuous functions is continuous. Therefore, what is there in the integral, inside the integral, that is continuous. Therefore, x2 is also continuous. So the well-definedness is easy, and moreover, the set of points that you take, t xkt, okay, for t lies in between this. So this whole thing is lying in the rectangle. This whole thing is lying in the rectangle. Okay, so what we were trying to show is, see, you have, we said that there is a rectangle here, okay, and there is a point t0, and we are finding the this is h, t0 minus h2, t0 plus h. So at this point, right, so we needed a curve like this which satisfies, so that is our aim. But these xn's, all of them also satisfy the initial condition, right? You can see that xk plus 1 at t0 is going to be x. So you have the functions within this t0 minus h to t plus h. This is all the x naughts, x1, x2, like this. They're all something like this. All of them passing through this. These are the xk's. Okay, so they're all satisfying this, and show that for t lying it in this, the t lying between t0 minus h to t plus h, the range of these curves, okay, they're all lying within the rectangle. Therefore, when I take f on this, that is going to be Lipschitz. Therefore, I can talk about, the idea of this is why we need this thing, is that I can talk about f of t x k t, okay, minus, if I want to estimate this, I can use this by Lipschitz continuity, okay, because now because I assume that f is Lipschitz continuous in the rectangle. Therefore, these variables have to be within the rectangle. These variables have to be within the rectangle. So for that, we'll show that this. Okay, so for that, we show that this. So this is the first step. This is step 1. So this is true for all k.
Please repeat step
1. Yes. Yes. What is that?
Repeat this part again.
I'm not getting, the voice break is there.
Sir, please repeat that.
Maybe you should write in the chat box, sir. In the previous example also, y equals to 0 is the solution. Okay, so you can write in the chat box. I'm not able to hear. There's a break in your voices when you try to speak.
Sir, he's asking for repeat. This part.
Repeat. Okay.
Yes, sir.
So why I need this this whole values to be in the rectangle is that my aim is to show that this some limits and things like that on f of s comma xks, right? So if I try to write any estimate on this, okay, any estimate on this using Lipschitz continuity, then I need that this xk's have to be in the rectangle, because we assume that f is Lipschitz continuous in the rectangle R. Okay, we assume that f is Lipschitz continuous in the rectangle R. That is why. Okay, so what is the rectangle that we took? We assume the rectangle is x t minus t naught less than or equals to, right? So that is our R. R is the t minus t naught less than or equals to a, and mod x minus x naught less than or equals to b. That's how we took the rectangular. Okay. So why this is true? So we know that f is bounded, right? So to show that this is going to be in the rectangle, mod t minus t naught less than or equals to a is a big number and h is a small number, because we are able to see that h is less than or equals to minimum of a comma b. Therefore, there's no problem for t minus t naught is less than or equals to a, because h less than or equals to a implies that t minus t naught, okay, is less than or equals to a. So that is trivial from this t minus t naught less than or equals to h. H less than or equals to a. So this part is clear. So other one we have to show is that xkt minus x naught. So this is what we have to show, right? So this is less than or equals to b. So why this is less than or equals to b is because this unite xk minus x naught is going to be integral t naught to t of f s xk minus 1 of s to ds. But this one is take the integral inside, the absolute value inside becomes like this, and this is less than or equals to m, because we assume that f is bounded on the whole rectangle. Therefore, this is less than or equals to m times t minus t. You can take f to be because it's a continuous function, we can take the bound on f in a much bigger set, don't be on this. So this t minus t naught is less than or equals to m into h, and h is less than or equals to b by m, so m into b by m, which is equals to b. Which is equals to. So this is now we have. Now come to the third claim, that is we will show now that xk converges uniformly to. Okay, so the next step is, or let me claim that xk converges to x uniformly. So xk converges uniformly. So once if we show that xk converges uniformly, then the limit is going to be a continuous function, because each xk is a continuous function. Therefore, the limit is also going to be a continuous function. So since we don't have what the x is, so the only way to go about here is try to show the Cauchiness, or try to show some kind of a some kind of Cauchiness. So because once if you know that if xk is uniformly Cauchy, then you have the xk converges uniformly. Right? So we claim that xkt minus xk minus 1t. So this is less than or equals to m by l into h power k by factorial k into l power k. For all t in for all t in this interval. So once if this is true, we will show this. We have not yet proved this. Once if this is true, then this actually implies that xk is a Cauchy sequence. Why is that? We'll prove this later. Once this is proved, then I can take the maximum, maximum over t naught minus h to t naught plus h of the same thing, right? So this is less than or equals to m by l into hk, sorry, h into l, hl power k by factorial k, right? So this one now, this is the infinity uniform norm, I said, xk minus 1. So if we show that this goes to 0 as k tends to infinity, then it is a uniform Cauchy. Right? So why this goes to 0? So this goes to 0 because this fellow goes to 0 as k tends to infinity. Why that fellow goes to 0 as k tends to infinity? Let us see that. H into L h into L power k by factorial k. So we can write this as HL by 1, HL by 2, like this, k plus 1 times, k times. Okay. So now you choose one, say n naught, such that n naught is greater than h into L. Then what this factor will become is h into L, HL by 2 up to HL by n naught, HL by n naught plus 1, h into L by k. So look at all these things. These are finitely many things. And this fellow is less than 1, and this fellow is less than 1, and this fellow is less than 1. So this is less than HL into HL by 2 to HL by n naught minus 1. So this whole thing is into one constant times this. All these things are going to be n naught power k minus n naught minus 1. Now you see that this fellow is less than 1, therefore power k, as k tends to infinity, this goes to 0. And this is simply a constant, okay, as k tends to infinity. Therefore, the HL power k by factorial k actually goes to 0. So that is now, which is now independent of your T naught. Therefore, this goes to 0 as k tends to infinity. So that shows that xk is uniformly Cauchy. Therefore, xk converges uniformly to a function which is a continuous function. Okay, so therefore, xk is uniformly Cauchy, and we saw that a uniformly Cauchy sequence is same as uniformly convergent sequence. Okay, so therefore this is uniformly convergent, and uniformly convergent sequences converge to a continuous function. Therefore, xk converges to x, which is x is continuous. Okay, so once if it converges, we could even take the xk plus 1, which is equals to x naught plus t naught to t f of s xks to ds. Take the limit on both sides. So when I take the limit, this goes to xt, which is equals to x naught, and this becomes again t naught to t. So taking the limit. So there will be a limit outside, that limit goes inside, comes here first, the limit of f. But yes, f is also a continuous function. Therefore, this limit also goes inside this f. So f of s into limit of xk, which is again, which is your x naught plus f of s comma x. So that is that becomes your solution. So what remains to prove now is this estimate. Okay, so this estimate. So let us look at this estimate. So we'll prove this by induction. So look at what is x1 minus x0. So x1t minus x0. Okay, from the given integral equation, we have this to be t naught t into f of x1 is x0 times ds. So this is absolute value less than or equals to f is less than or equals to m times going to be mod t minus t naught. That's what we have for this. Look at x2 minus x0, x2 minus x0, x2 minus x1, x2 minus x1. So x2 minus x1, okay, is going to be x0 and x0 gets cancelled. F of s comma x1, right, minus f of s comma x0. So this is less than or equals to t naught to t. Right. So we know that now f is ellipsis on the rectangle, and this x1 and x0 both are going to be in the rectangle. Right? Both are going to be in the rectangle. So that you can see here also that this is why this is in the x1 is in the rectangle. Already we proved it, but again, which is less than or equals to. Therefore, it is in the rectangle. Therefore, I can apply the ellipsis continuity. So this is T0 to T, okay, into mod x1 minus x0. x1 minus x0, from this step you have m into t minus t0. So this is going to be, right, so m into L by 2 into t minus t0 whole square. So that is what we have the claim there. So this is true, the estimate is true for 2. Now assume for by induction, assume for say n, and then write for assume for k, and then write for k plus 1. For k plus 1 we have xk plus 1 minus xk. Okay, so this is again less than or equals to mod f of s comma xk minus f of s comma xk minus 1. This is less than or equals to L times mod xk minus 1. And for at the step k, we have an estimate for xk minus 1. That is less than or equals to L into what we assumed, m by L, okay, into mod t minus t0 over k, okay, upon factorial k into L power k. Right. So this again integral. So this is nothing but L power k is there, so you can write L power k plus 1 to m by L, and this is t minus t0 power k plus 1 by k plus 1 factor. So this estimate is also true. Therefore, claim follows. So this is by induction. We do this. Okay. So what is that? So now we have the existence that because the series now the xk converges to x converges uniformly. Therefore, it converges to a limit which is a continuous function, and it satisfies the integral equation. Therefore, it becomes a differentiable function because once it satisfies the integral equation, we can differentiate it because by the fundamental theorem. Right. So the next is about the uniqueness. Why there should be only one solution. Uniqueness. So consider. So let T naught be less than delta be such that the ellipsis constant times this delta is less than 1. You can always do this. Choose your interval within this t minus t naught less than h. Okay. So you have the t naught, and this is t naught minus h to t naught plus h. Within this interval, you take another small interval. So this is the delta interval. Okay. So that L into delta is less than 1.
Voice is breaking.
Yeah, that may be because of the network, but you can see later that it is recorded anyway. So if xt and yt are two solutions, if xt and yt are two solutions, write xt minus yt. Okay, so both of them satisfy the differential equation, and therefore both of them satisfies the integral equation. So this becomes the integral, okay, t naught to t f of sx minus f of sy. Okay, so write the estimate on both sides. So this is less than or equals to take the absolute value inside and use the ellipsis continuity. Get t naught to t of x minus ys. Okay. So take the maximum or the supremum of this. So let me write this as xt minus yt. I'm taking the maximum outside the integral times mod t minus t naught. So this is now a constant, and what we have is L into delta, right? So this is L delta into the norm x minus y. And because now it is a constant on the right hand side, so you can take the supremum on the left hand side. So this also becomes this, and you cancel this, you get 1 less than L delta. Okay, so if you have any questions, quickly you can ask in the next 2 minutes, otherwise I will stop it here. Do you have any questions?
Sir, as you provided series 1 for earlier, for previous topics, are you going to provide something for this also?
Yes, I'll provide.
Sir, will you take our today's tutorial class?
See, there is a TA, so she has gone home. I don't know what is her state now. So we'll start some tutorials maybe this week, and maybe if request, she will take extra tutorials.
Okay, sir.
She will write an email to you, and we will be in touch with you. Okay.
Doctor.